We will start today to do review problems on rigid body equilibrium. So first, in the first problem, the C bracket is supported at A, B, and C by rollers. Determine the reactions at the support. So when you have equilibrium, you can have 2D or 3D problems, okay? If you have a 2D problem, then you can write 3 equations of equilibrium. So first, we should determine the unknowns. We should draw what are the reactions we have. Since we have 3 rollers, okay, we have seen together that for rollers, the force is always perpendicular to contact. So here at A, this is the contact line. So the reaction at A is perpendicular to the contact line, okay? So this is the contact line and the reaction will be like this. This is RA. Now, at B and C, okay, you have a circular track of radius A. When you have a circle, you have always that the tangent is along the perpendicular to the radius. If I want to draw the contact line, it is perpendicular to the radius at B and also perpendicular to the radius at C. Okay, so the reactions will be like this. This is reaction at B, and this is reaction at C. Okay, so now I have the 3 unknowns, RA, RB, and RC. Okay, and I want to calculate my unknown, so I should write 3 equations. I have, as we have seen in the course material, we have several possibilities in writing the 3 equations. You can choose, for example, 2 force equations, 1 moment. You can choose 2 moment equations, 1 force equation, or 3 moment equations. So you can do sum of moment about A0, sum of moment about B0, and sum of moment about C0. So it depends which equation is easier, you will select. First, if you want to choose a moment equation, try to choose sum of moment about a point for which we have a lot of forces having 0 moment. For example, here, if you take this point, the center of the circle, point O, what can you say? You can say that RB and RC are passing by O, so they don't have any moment about O, okay? So it will be a good idea to take sum of moment about O equals to 0. So if I want to do sum of moments about O, I have the moment of RA and the moment of F, okay? So first I should select a positive direction. I can consider, for example, that the counterclockwise is positive. So I will put this. I will say this is my positive direction, the counterclockwise. Then if I do sum of moments about O, what do I get? Sum of moments about O equals to 0. I have the reaction at A, so RA times which distance I should multiply by? This is the line of action of the force, okay? I can take a parallel from O. The distance between the two is A, so I should multiply by A. And it's positive because it's doing a moment in the counterclockwise direction. Now for F, F is rotating about O in the clockwise direction, so it's minus. And I should multiply F by the distance from O to the line of action of the force. This distance is equal to, as you can see in the figure, to B. Okay, so I do here minus F times B equals to 0. Okay, so this is equation number 1. From equation number 1, I can get RA because F is given, okay, and A and B are known, so the only unknown is RA. So I find from this equation I can find RA. Okay, now once I have RA, the next step is I can write now, if you want, sum of forces along x and y. Okay, if I do sum of forces along x and y, I will obtain two equations with two unknowns, which are RB and RC. So let us write together the equation along x. Along x direction, what do we have? RA and F do not have any component along x direction. I have only the components of RB and RC. If you look at your figure and you project RB and RC, it can be seen that RB has a positive projection along x, and it's equal to RB sine theta 1, okay, because the angle of the reaction with y-axis is theta 1. And for RC, it has a negative x component, and the component along x is RC sine theta. So if I write the equation along x, I have sum fx equals to 0. I get RB times cosine of theta 1 minus RC times cosine of theta 2 equals to 0. Okay, this is my first equation between, and if you want, it's equation number 2, because the first equation gave me RA. Now, the second equation, I can do sum Fy equals 0. So if I do sum Fy equals to equals to 0. Along y, what do I have? I have minus RA minus F minus RA minus F, and I have RB and RC, so I should project them along the y direction. You can see that both have positive component along y. So this is RBY and this is RCY. Okay, so I can write here that it is equal to plus RB cosine. Just please here, when we wrote sum of x, just we should put sine. Okay, pay attention for this. So here, because we said that it's sine, but when we wrote the equation, we put cosine. So for the x, it's sine. It's sine the angles along the x. Okay, and along y, it's cosine, because the angles given are with y-axis. So plus RB cosine theta 1 and plus RC cosine theta 2 equals to 0. Okay, now you end up with equation 2 and equation 3 contains two unknowns only. So I can solve for two equations with two unknowns. I get RC and RB, and I am done. I have found RA, RB, and RC. Okay, any question for this? Okay, so let us move to another problem. The car is being towed at constant velocity up the incline using the cable at sea. The car has a mass M and center of mass G. The tires are free to roll. Determine the reactions on both wheels A and B and the tension in the cable at sea. Okay, so here in this problem we have the force in the cable F. We have the weight of the car. Okay, now they said that the wheels are free to roll, and when they don't give any information about friction, you can consider that the mass of the wheels is negligible, and you can say that no friction. Okay, so we have only normal reactions at A and B. Okay, and what we want to find, the unknowns are the reactions. We need to find what are the reactions. Okay, so here we have RA and we have RB. Okay, and we have the weight, which is equal to mg. Okay, and we want to find what is the reactions at A and B and the tension in the cable. Okay, so here if you want, they said that the car is moving at constant velocity. So we have motion. It's true that we don't have an equilibrium state. It's not at rest if you want, but we have what we call dynamic equilibrium. So it's in motion, but without acceleration. Okay, so we have in general two types of equilibrium. Static equilibrium, this means that it is fixed, and dynamic equilibrium, this means that it is moving but without acceleration. So when it is moving without acceleration at constant velocity, we can still say that we can apply that sum of forces is equal to 0. Okay, and we have in this problem 3 unknowns: the tension force F, the reaction at A, and the reaction at B. So we need to write 3 equations: sum of forces along x equals 0, sum of forces along y equals 0, and sum of moment about any point you choose equals to 0. Okay, now to start with, you can choose x and y as you like. So for example here, it is easier to choose xy like this. I can choose x upward and inclined. Okay, so but whatever the frame you choose, at the end you will have same forces. Okay, but here it might be easier to work in this frame because as you can see, RA and RB are along y-axis, which is perpendicular to the frame, and F, they gave us the angle theta with the incline. Okay, so it is a good idea to choose the frame like this. So this is X, and this is Y. Okay, now in this frame, if you want to write our equations, first we have to, let's say we want to apply sum of X. Okay, we want to apply sum of X equals to 0. To start with, what are my forces along X? Look at the figure. What are the forces having component along X?
F and the weight.
Tension and
Very
weight.
good, F and the weight. Okay, so here for the force F along X, what is the component? F cosine theta. Since I choose X upward, okay, then it's along X, it's plus F cosine theta. As you can see in their solutions, I considered minus F cosine theta because they considered X downward. So you can take your system as you want, but you should follow your sign convention. Okay, if you take X upward, then F has a positive component along X. Now for the weight, we should project the weight on X direction. This is why we need to find this angle here. Okay, because we need it for projection. We needed to find the component of weight along X. In order to find this angle, we have several methods. Okay, the first method is to say that I will clear the drawings to make it clear. Okay, you can say that the weight is along the vertical. Okay, the weight is along the vertical line, and the vertical line, of course, is perpendicular to the horizontal. Okay, so since the angle here is theta 1, then the angle of the weight with the incline, which is the x-axis, is 90 minus theta 1. Okay, and the angle of the weight with y-axis is theta 1. Another method to prove this is to say the following: the weight is perpendicular, which is along the vertical, is perpendicular to the horizontal, and From the other side, you have that y-axis, this y-axis, is perpendicular to x-axis, this one, to this line. So this line here, y, is perpendicular to x. And you have, from math, you can say that if I have two lines doing an angle theta 1, and I draw the perpendicular to the first and the perpendicular to the second, then the angle between the two will also be theta 1. So again, you have proved in another way that the weight is doing an angle theta 1 with y-axis and 90 minus theta 1 with x-axis. Okay, so now when you project, you have a negative projection for the weight, and you should multiply by sine theta 1. Okay, so the formula along x will be f cosine theta 2 minus mg times sine theta 1. Okay, equals to 0. Now, second equation along y. Okay, along y, if we put again the forces, you have RA, RB, and you have the projection of F and the projection of weight. Okay, so along y we have a plus RA plus RA plus RB plus F sine theta 2, and only the weight has a negative projection, so it's minus mg times what? We said that the angle of weight with y is theta 1, so times cosine theta 1. Okay, equals to 0. This is our equation number 2. We still have to write one equation to close our system. Okay, the equation will be an equation of moment. Okay, you can choose any point in your figure and do sum of moment about this point. So let us see what can be a good point, for example. For example, if you want, since the force F is passing by C, and it has two components, one along X, one along Y, we can choose to do sum of moment about C equals 0. And then we cancel out the moment of F, for example. Okay? If you want to do this, then we have to take into consideration the moment of all other forces about C. So we have the forces and we have the weight here. Okay, so now we have first the moment. Let us consider the counterclockwise direction as positive. So I will put here that I will take the counterclockwise as positive, and I will do sum of moment about C equals to 0. Okay, what do I have? First, I have the moment of RA. RA is producing a counterclockwise moment, and I should multiply by this distance, which is given to be D. I multiply by D. Okay, now for RB, I should consider the distance from RB to point C, which is D plus C plus B. Okay, so I have until now plus RA times D plus RB times D plus C plus B, D plus C plus B, and I still have the weight, the components of weight. Okay, the moments of weight components. Now for the weight, I will decompose it into two parts, the y component and the x component. As you can see in the figure, the x component is passing by, oh no, it's not passing by C, look, because G, the center of gravity, is above C. Okay, so as you can see here, this is Wx, okay, and we have a certain distance between Wx and C. So let us look at the figure here. Okay, you have that this distance here, you want to find this distance, this one. Okay.
C minus A.
Yes, it is C minus E minus A. Okay. This distance is E minus A. And as you can see in the figure, the x component, if you do the right hand rule, okay, is also producing a moment in the counterclockwise direction. So it's a positive moment. So plus, what is the x component we said of the weight? It's plus mg times sine theta 1 times sine theta 1 times the distance, which is e minus a, So we still only have the moment of the component of weight in y. This is the y component of the weight. The only component doing a clockwise moment is the component of w along y, so it's a negative moment. Okay, so and I should multiply it by the distance. The distance from y component to c is this one. Okay, this distance is equal to what? To d plus c. Okay, so I should do here minus mg cosine theta 1 times the distance c plus d, okay, times c plus d equals to 0. So now I have until now 3 equations with 3 unknowns. It's a system, so I can use my calculator to find my 3 unknowns. Okay, any question on this problem?
Doctor, please, can you repeat الويت كيف جبنا لها ال x and y component?
Yes, of course. For the weight is along the vertical. Okay, this is the direction of the weight. Now, how to project the weight on x and y? You need to find the angle, yes? So you need to know what is the angle of the weight with x, and x is along the inclined line. In the figure, it is given that the inclined line is doing an angle theta 1 with the horizontal, okay? But since the weight is perpendicular to the horizontal, then the angle between the weight and the horizontal is what? Is 90, okay? So if you know that this is 90 and this is theta 1, what will be the angle between the weight and x-axis? In a right triangle, the summation of the is 90. So this is 90 minus theta 1. Okay. So since the angle of the weight with x-axis, which is inclined, is 90 minus theta 1, then the angle of the weight with the perpendicular to x, which is y-axis. So if I present here y-axis, which is perpendicular to x, this angle here will be what? Because the total angle between y and x is 90. And since the angle of the weight with x is 90 minus theta 1, so the angle between the weight and the w will be what? Between the weight and y will be theta 1. Okay? So when you project on x, you do cosine 90 minus theta 1 or sine theta 1. And when you project on y, you do cosine theta 1. Okay? Is it clear now?
Yes, thank you.
Okay. Okay, another problem. A table has a weight WT and a center of gravity at GT. If a man weighting WM has a center of gravity GM and sits down in the centered position shown, determine the vertical reaction at each of the 2 legs at B. Neglect the thickness of the legs. What can you conclude from your results? Okay. So here we have a certain person sitting on a table, okay? And we want to compute what will be the resulting reaction at legs. So we have 2 legs at A and we have 2 legs at B, okay? So due to, if you want here, we can put, we have 2 times RA because we have from the other side another leg, and due to the symmetry, because the person is at the middle of the table, they told us that it is sitting in the centered position, then the reaction in the two legs are equal, in A legs and in B legs. Okay, so it's 2RA and 2RB. Now, we have also the weight of the man passing by its center of gravity, and we have also the weight of the table. Okay, so this is W man, and this is W table. Okay, now they want us to find what is the reaction in legs B. To find the reaction in legs B, what is the easiest equation to use? Who will tell me? If you want to write one equation that will directly give you RB, what equation to use? Look, how should you think? We know the weight of the man, okay? And we want to express the reaction function of the weight of the table. But since we have another unknown, which is the reaction at A, it will be a good idea to do sum of moments about A. Because when we do sum of moments about A, the reaction at A will not have a moment, okay?
0.
So 0. So we only have then the moment of the resultant of the two legs B. Okay. So what we can do here is that we can say that sum of moments about A equals to 0, and this will give us. Let us choose a positive direction. We can choose the counterclockwise direction as positive. So I consider the counterclockwise direction as positive. What do we have? We have that the reaction at B is doing a positive moment. It's turning in the counterclockwise direction. And I should multiply by the distance, which is B plus C. Okay, so I have 2RB times B plus C. Now, for the weight of the table, it's having a moment into the clockwise direction. Okay, so it's minus WT times which distance? If I look in my figure, the distance between this point and the weight of the table is equal to B. Okay, so it's times B. Now I still have the moment of the weight of the man. As you can see here, the weight of the man is producing a moment into the counterclockwise direction. So it is positive, a positive moment. So plus weight of the man times the distance between the weight and the point A, which is what? If I look here, if I take the parallel to the weight from A, okay, I have that this distance here, I need to know this distance. This distance is equal to A, okay? So I do plus W man times A equals to 0. So now, what I want to find is the reaction at B. All I have to do is to take these terms to the other side. So I end up with the following relation. I end up with the reaction at B is equal to W table times B minus W man times A over 2 times B plus C. Okay? Now, they told you what can I conclude from the result. What they mean here, when we do a table, we should design it in a way to support a big weight without tipping over. Okay? So for example, if it's designed to hold, for example, from one side 3 persons, Let's say we say that we will design based on 300 kilograms from one side. We should not have tipping over. Okay, what do I mean by tipping over? If you have a large weight here, you have a risk of turning the table about which point? About point A. Okay, so you risk of losing contact with point B. To not lose contact with point B, what is the condition? In order to keep a contact with a surface, you should keep a reaction, a normal reaction between the surface and the table. So the condition to keep contact is that NB is higher than 0. Okay? Once NB is equal to 0, this means that you will start to lose contact with your ground. Okay? So you will say that the condition to not lose contact is to have this ratio higher than 0. So you can find a condition on the weight of your table. Okay? So the condition here is to have this term higher than 0. This means that 20 WT minus 1,350 should be higher than 0. Okay? If it is the case, you have equilibrium. If it is smaller than 0, then you will have tipping over. Okay? Any question on this? Okay.
Doctor,
Yes?
نحن we put 2 times the reaction at A and B لأنه في 4 table legs.
Yes, because you have two at, if you want, this is the center plane we have considered here. Okay? The occupant is just at the middle. So you can say that you have a resultant reaction due to symmetry. Your resultant reaction will be in this plane and it's equal to 2RA here because you have two legs. And here the resultant of the two legs at this side is 2RB passing by the center plane.
Okay, thank you.
Okay. Any other question on this problem? Okay, in this problem, we have a lever that is pinned to a fixed frame at A and held in place by the spring, which has a non-stretched length delta. Determine the magnitude of the resultant force at A and the normal force on peg at B when the lever is in the position shown. So here, we have, this is our lever. The lever is connected to a spring and it's in contact with a roller at B, okay, and a pin at A. How do I know this? I know from the figure, okay? So from the figure, when you see like this, when you have a member, when you have a certain member and they put a circle inside, this is a pin, okay? It's like a screw if you want. A screw that is not allowing for displacement in X and Y. This is why at A, you have two reactions in X and in Y, okay? Now, at B, it's a roller because you have a circular shape just at contact with the arm, okay? So this one here, this one is a roller because it can only develop a reaction perpendicular to contact. So here you can say that the force will be like this. While for a pin you have two reactions because it will not allow motion in X and it will not allow motion in Y. Okay? And we have also the spring force. So the first step in the problem will be to draw the free body diagram. In the free body diagram, I will show all forces acting on my system. What are the forces? As we said, we have, you can see here, we have the pin at A, so we have AX, AY. Now, how to choose for AX, AY? You can choose any frame, the frame that is convenient for you. A good idea is to take X-axis along the bar and Y-axis perpendicular to the bar. So you will have like this, AX and AY. Now, at B, you have a roller, so you have a reaction perpendicular to the bar, so it will be along Y-axis, so this is NB, and you still have only the tension of the spring, and the tension of the spring will be directed along the spring, okay, so it will be like this. So until now, we have a problem because we have 4 unknowns. We have AX, AY, and B, and the tension of the spring. But for the tension of the spring, how can I find it? How can I find the tension in my spring? What should I do?
Sum of moments on A?
No. What I mean, look, what I mean here, you already have 3 unknowns, AX, AY, and NB, plus the tension. So you have 4 unknowns. So it's not enough to think about the 3 equilibrium relation. We need a 4th relation. The 4th relation, we can get it from the property of a spring. You know that for a spring, the developed force is equal to what for a spring?
K delta L.
Yes, exactly. So force of the spring is equal to K times delta L. So if I find delta L, then I will reduce my system to 3 unknowns, and I can write 3 equations with 3 unknowns, okay? So now before writing the equilibrium equation, I will try to find the tension force. This is why I should find delta L. They gave me the the unstretched length of the spring. The unstretched length of the spring is delta equal to 200 millimeters. So this is L0, okay? To find delta L, you know that delta L is equal to what? So this is K times the final length, L final of the spring, minus L0. Since I know L0 and I know K, I still only need to find the final length of my spring. This is why I should look at my figure and use geometrical properties to find, this is the final length at the position given, okay? So I can find this length from geometry. So if you remember the chapters, the first chapters we have done together, we learned how to find a length in a triangle. As you can see, this length is in this triangle. We know that the distance here is C, and we know that the distance here is, this one is A plus B, okay? So we still only need to determine one angle, but as you can see in the figure, this angle here is equal to 180 minus angle theta, and angle theta is given. So if theta is equal to 30 degrees here, then this angle is 150. So now you remember which law I can use to find L? Look in this triangle. I know A plus B, I know C, I know the angle in between. I can use the cosine law to find L, okay? So when I use the cosine law, I can calculate the length L final of the spring. L is radical of C squared plus A plus B squared minus 2C times A plus B times